We would like to be able to find the area of the region between two curves. Let's start with two curves. Uh, the first curve is a graph of the function y equals f of x. This is a very simple function and it's all positive. It's above the x-axis. So let's consider a region from A to B. The region under the curve from A to B. Like this. So we're looking at this region. Well, I'm going to color it green. And I'm going to call this region A, maybe AF, like that. And then let's look at another function, y equals g of x. And we want to consider the graph of this function. And we want to consider the area under the graph from the same beginning point A to B. Let's color with green again. Okay, now let's call this area, let's call it AG. Now we have the graph of y equals f of x and the graph of y equals g of x, and we would like to find the area between the two curves. So what area am I thinking of? Again, I'm going from A to B. So I'm thinking of this area. I'm going to call this area A. Now visually, we can make some conclusions. First of all, let's think back to Calc 1. AF can be calculated as the integral from A to B. AF, the integral from A to B of f of x dx. AG can be calculated as the integral from A to B of g of x dx. Now, just looking at this visually, the larger area is AF, the smaller area is AG. A is in between AF and AG. And if you look at this visually, you can conclude that to find A, we just have to subtract AG from AF, right? So A over here is AF minus AG. Okay. So this allows us to write up a theorem. So let's consider two functions. Suppose f and g are continuous functions, just like in our examples. Continuous functions with f of x being greater than or equal to g of x on the interval a to b. The area between or let's do it this way. The area of the region bounded by the curves y equals f of x and y equals g of x on the interval AB is given by a equals the integral from a to b of f of x minus g of x dx. So how did we arrive here? Pretty easy. Let's go back to a over here. We know that a is af minus ag. So let us derive some things. So this is the same thing as af, which is the integral from a to b of f of x dx minus ag, the integral from a to b of g of x dx. So this can easily simplify to the integral from a to b of f of x minus g of x dx. So that is how we got this, right? So in general, you can think of this as I'm going to write in green, as a as being the integral of the top function minus the bottom function dx from a to b. All right. So f is the top function and y is the bottom function. Let's do a few examples. Number 1. Let us find the area of the region bounded by or bounded above by y equals x squared plus 1 below by y equals x and on the sides by x equals 0 and x equals 1. So let's sketch these curves. It's always important in this topic to sketch your curves. So let's sketch as many as we can. So we have y equals x squared plus 1. So that's just the parabola y equals x squared shifted up 1 unit. So let's assume this is our 1 unit. We have the parabola. And then we have y equals x. It's just this line. So this is y equals x squared plus 1. This is y equals x. And then we're going from x. This is the x-axis. So this is where x is equal to 0. And then we're going up to where x is equal to 1. All right. So we're trying to find the area in this curve, in this region A. call this area, call this region A. Okay. So we already know how to go about this. We find the area by calculating the integral from x equals 0 to x equals 1 of the top function minus the bottom function dx. So our area in this case that we're looking for, area A, is the integral. The top function is x squared plus 1, and then the bottom function is x. And we're calculating the integral from 0 to 1. So this is equal to the integral from 0 to 1 of x squared minus x plus 1 dx. And then if you perform this integration, you get x to the power of 3 over 3. So you just add 1 to the exponent and divide by the result, minus x squared over 2 plus x. And you go from 0 to 1. You plug in 0 and you plug in 1 and you subtract. So if you plug in 1, you get 1 over 3 minus 1/2 plus 1. If you plug in 0, you just get 0. So if you add up everything here, you get 5 over 6. So how did I do it? The common denominator is 6. So 1/3 I can write it as 2/6. 1/2 I can write it as 3/6. And 1 I can write it as 6 over 6. So this is 5 over 6. Okay. All right. So I would like you to try one on your own. I would like you to try, let me write it out. Call it number 2. I'd like to find the area between the parabola y equals equals 2x minus x squared and y equals x squared. I'm going to sketch it for you. This is what the graphs look like. So we begin with y equals x squared, which is easy. Y equals x squared. Let's do this. And then y equals 2x minus x squared. Looks like this. Looks like that. So this is y equals 2x minus x squared. So first of all, you have to find this point. What is this point? Right? I'm going to call this B. Okay. So the region you're looking for is this region. And I'm going to call it A. Okay. So the first thing you have to do, I'll write this out in green. First, find P. And how do you find P? You find P by setting, you want to set the two functions equal to each other. Set x squared equal to 2x minus x squared and then solve for x. Okay. And then after doing that, then you can do your area. Your a is just going to be the integral from 0 to whatever p is. I can't tell you, or I won't tell you, of the top function x squared minus the bottom function 2x minus x squared. If you do this correctly, I think you will get, I got 1/2. I want you to check my answer to make sure it's correct. Actually 1/3, that's what I got. All right. Okay. Let's do another problem. A third problem. Number 3. Let's find the area of the region between the graphs. Oh no. The graphs of f of x equals x plus 3 and g of x equals absolute value of 2x. So the absolute value function, remember what it looks like. Let's recall what the absolute value function looks like. Or let's dissect it. So let's recall that g equals absolute value of 2x can be defined as a piecewise function. What does this mean? This means that if x is greater than 0, this function is simply 2x. If x is greater than or equal to 0, and it's negative 2x if x is less than 0. Okay. So that's what you have to begin by doing. So this should help you think clearly about the graph of this function. So let's try to draw it. So we have that. The y and the x-axis. All right, so this is, let's make this 1, and then 2. So we have, this is our function g of x when x is greater than or equal to 0. And then when x is less than 0, it's negative 2x. So this is 2x, call it y equals 2x. And this is y equals negative 2x. And both of them come together to make the function g of x. Okay, so we have another function, y equals 3x. All right, so I'm going to do something. I am going to move my function down a little bit. So I'm going to draw the line, extend it, and extend this one, and I'm going to rotate this just a little bit now. They don't look symmetric to me, so I'm gonna come like this, and then I'm gonna draw it more. Oh no. Draw it like this. Draw it like that. And then go, oh shoot. And then, oh no. Go like that. Okay. You guys can see I'm struggling a little bit with this, but it's okay. So this is 3. So this is y equals 2x. This is y equals negative 2x. And we have y, our f of x is y equals x plus 3. So we have to x plus 3. So we have to go like this. All right, so this is y equals x plus 3. This is our f of x. So the area we're looking for is actually this area. But what I want us to do is I want us to think about this as 2 areas, and I'm going to explain why. Let's think of this as A2, think of this as A1. Okay. So if we think of it that way, it's easier for us to manipulate. Because our area now, the area we're looking for is A2 or A1 plus A2. Why am I writing it this way? Because from this point, whatever this point, this point to over here, this line, you have x plus 3 at the top and negative 2x at the bottom. And then from this x-axis to over there, this point right here, you have 2x at the top and then x plus 3 at the bottom. So we have our work cut out for us. We can't just do the integration right away. We need to find what these points are. Call it P1 and call it P2. All right? So first of all, let's look for P1. To find P1, to find P1, we need to set negative 2x equal to x plus 3. Right? If you solve this, I'm going to solve it really quickly. If I take x to the other side, I just get 3x, and then bring x to this side, I get negative 3. So x is negative 1. And then let's solve for P2. We just need to set 2x equal to x plus 3. If you solve this, you're just going to get x is equal to 3, I think. All right, so what does this tell us? This tells us that we have to extend this line a little bit. We don't have to, but it will make sense to extend it a little bit. And why am I extending it? Because if I go down here, I now know that this is 3. And this over here this is -1. So we're integrating from -1 to 3. So that our A1 is a region that goes from 0, from -1 to 0, -1 over here to 0 over there. And then the top function is x plus 3 minus the bottom function, which is -2x, and then dx. So that's A1. And then you add A2, the integral from 0 to 3. The top function here is x plus 3, and the bottom function is 2x. So you subtract 2x. So when I did the first integral, I got 3 halves. And then the second integral, I got 9/2. So if you add both of them up, you end up with 12/2, which is the same thing as 6. So I would like you to check your integrals, check your integration, or check my integration in this case. Okay. All right. All right. Let's look at a fourth one. So we'd like to find the area enclosed by the line y equals x minus 1 and the parabola y squared is equal to 2x plus 6. All right. So there might be questions already, or they may not. But let's look at this. We have y equals x minus 1. It's a line that passes through the x-axis. No, it doesn't pass through the x-axis. It passes through x equals -1. All right. I should be careful what I say. All right. So we have this line, straight line. Its slope is 1, passes through -1, right? Positive slope. So this is y equals x minus 1. Now, this is a function that it's called a parabola, but we're used to having an x squared in a parabola, but this is still a parabola. Why? Let's solve for y in this function, or let's solve for x. If you solve for x, you end up with y with x is equal to 1/2 y squared minus 3. This is a parabola. And why is it a parabola? Because if you treat the x-axis as your vertical axis and then treat the y-axis as your horizontal axis, you end up with a parabola. So this is just a parabola that is a little wider, but then you move it down 3 units. So in this case, you're moving it to the left 3 units. So instead of being over here, it becomes somewhere over here. Its vertex is at -3 on the x-axis. So let's complete this parabola. There's something like that. All right. So we have an area. This is our area A. Now, if we want to find out this area A, and we want to integrate with respect to x, the best thing to do is to divide up our function, or divide up our area. From this point to this point, we have to look at this graph as a top function and that as the bottom function. And then from this point to that point, we look at this as the top function and that as the bottom function. But that's very complicated to do. Alternatively, what we can do is to flip this graph. I'm going to flip it, and you see what I'm talking about. I'm going to copy it, and then I'm going to paste it over here to show you what I mean. Okay, if you look at this, this is almost what we want to envision. But think about this. This is now your positive horizontal axis is on the left, right? And your negative horizontal axis is on the right. So instead of thinking of this graph as, let's go back to the large one. Instead of thinking of it as top minus bottom, it's better to think of it as right minus left. Because that way, we have just one graph. Instead of dealing with two graphs, here and here. Okay. So, I'm going to delete this. I don't want it to confuse us. So we're going to think of this as our integral A the top function is y equals x minus 1. But since we're going from left to right, or since we are envisioning the x-axis as our vertical axis, it's good to rewrite this as a function of y. So this becomes, this function becomes, we can write it as x equals y plus 1. And then this one, this was originally y equals, or y squared equals 2x plus 1. We can rewrite it as x equals 1/2 y squared minus 3. So in this case, our integral is going to be right. Instead of top minus bottom, it's going to be right minus left. dy. But we would like to know our y's, the y that we're integrating from. We're integrating from here. Let's call this d. Or we're integrating up to there. And let's call this c. So we're integrating from c to d. How do we find c and d? All right, to find c and d, you want to set the two equations equal to each other. So you want to set y plus 1 equal to 1/2 y squared minus 3. And then you want to solve for y. If you solve for y, you're going to end up with y equals 4 and y equals -2. All right, so this is actually -2 and this is equal to 4. All right, so our integration is just going to be the integral from -2 to 4 of the right function. The right function is now y plus 1 minus the left function 1/2 y squared minus 3 dx, actually dy, sorry, dy. So if you do this carefully, it involves being patient and expanding everything and doing the integration, dy, not just y. If you do the integration really well, well, let's expand it more a little bit. You get y minus 1/2 y squared plus 4, I think, dy. Right. If you do this integration and you manipulate it really well, I got 18. So I want you to check the answer. 18. Okay.